Okay, so if there are no questions, let's jump into the topic for today. As I mentioned last time, we are going to start with one type of learning exercise, and it actually is one of the fundamental learning tasks in machine learning. It's called concept learning. And we are going to look at a problem setting which is fairly straightforward, and I'll tell you how it can be made more complex. But the reason we are going to start with that simple setting is because that will allow us to analyze algorithms, right? This is a computer science class. We are all about the analysis of these algorithms, right? How fast they work, will they converge or not, how much data do they need to learn to be able to learn reliably, what is the notion of reliable learning, and so on, right? So these are all the questions that we want to talk about. What you will see is that none of these algorithms, the ones that we will do this week, today and next week, are very practical. So it's unlikely that you will be using those methods ever in life. But the reason we look at these is because they will help us sort of understand the fundamentals of machine learning. Of course, once we go into more complex settings, the analysis becomes much more challenging and more involved. So that's not the scope of this class. All right. So what is concept learning? So the notion of concept. Let's start with concept. So there's this term called concept, and I'm sure you are all familiar with that. Okay. Concept. So concept is just sort of is what it means, right? It's some kind of a notion. And the idea is that every object you can, or a concept is essentially something that defines an object. For example, a chair, that could be a concept. So something is a chair, so that means it belongs to a concept, or something might not be a chair, which means it does not belong to a concept, right? Mathematically, you can think of, so, or in machine learning, what we want to do is, we want to, given a concept, we want to acquire an ability to be able to take any object and say if it belongs to a concept or does not belong to a concept, right? So there's any object, so there's a notion of a concept, and there is a notion of a data object. Okay, typically I will use small alphabets like X to denote an object, right? So any object can either belong to a concept or or not belong to a concept, right? So it's X can belong to a concept, and we'll denote concept with letter C. So it can belong to a concept C or not belong to a concept C. So or. So you can also think of it same as we were talking last time as a label, right? So if something belongs to a concept C, it will have one label or one class. It does not belong, it's another label or another class, right? Because I don't want to write belong to a concept over and over again, so we'll use some shorthand notation. So if X belongs to a concept C, we will say that its label is 1. And if it does not belong, its label is 0. Right? If you pick up any machine learning textbook or any paper that talks about machine learning, one thing you'll notice is that they abuse notation like anything, right? So sometimes you might even see that if it belongs to a concept, they say it's +1. If it does not, it's -1. It means the same thing, right? Sometimes you might even see true and false. So if it belongs, it's true. If it does not belong, it's false. I will try to be faithful to one notation, but sometimes I might stray. So let me know if things get confusing. But the idea is that what a concept does is it essentially labels a data object into one of two types, right? So it's a binary concept. And an example is a chair, right? But for the same object, you could have multiple concepts. So the concepts are not tied to the data, right? So for example, I could have a concept which I can apply to this object, which is a chair, and this will be false. Or I could also apply a concept is living being, and that also could be applied to this. Or another could be is made of wood, so that could be a concept as well. So you could have different concepts. So the task of machine learning is learn those concepts, and the idea is that if we have that concept, then if I get a new data object, right, I can apply the concept to that and say it belongs to this concept or it does not belong to this concept, right? Very similar to the example we saw on Wednesday. Okay. Any questions so far? All right. Now the next thing is, I completely lost my train of thought. Okay. So let's start with an example. All right. So we have not talked about X at all. Like, what is data? Now, in last class, we saw that we want to X will be represented in some way, right? We can't just take tables and chairs and just put it in the machine. We want to represent it, and we represent it using a set of features, right? So typically, what we do is we say X can be written as a bunch of features, right? So some few features. And these features describe each data object, right? So let's take a very simple example. Let's say there is some hypothetical object that we have, and I have some cards here, right? So let's say that the object that we are considering in this example are described using 4 features. So the features are shape, size, like color or darkness, and surface type. I'm just making these things up, of course. Okay, and let's assume that there are only four features that describe an object, and let us also assume that each of these features can take one of 2 values. Okay, so that's the first simplification that we do, that let's say shape can only be oval or circular. Let's say size can only be large or small. Color can be dark or light, and surface type can be smooth or irregular. Yeah, so that is how we will simplify our problem, that each object is defined using 4 attributes or 4 features, and these features are binary because they can take one of 2 values. Yeah, so that's a very simple case. In real life, typically you won't have such a simple setting, right? But let's say it is, yeah? Which means that now now I can have different types of objects, right, which take different values. If I put them all together, I call that a data set. So I'll represent that set by a calligraphic X, and X contains all the possible objects that can be using these 4 features. All right, so a question for you is, how many objects can I have in X? How many objects can I have in this big X? Louder? 16? Yeah, so I hear 16. And yes, so you can have 16 possible objects because each feature can take one of 2 values, 2 times 2 times 2 times 2, so it's 16, right? So what I've done here is I've prepared these cards. Each card is an object essentially, and this I've written the 4 values that are there. Yeah, so oval, large. This one is oval, large, dark, irregular, oval, large, light, smooth. So you can have all possible combinations. You can't have repetitions. It's a set, right? So this is your big X. These are all of your values. Yeah. So now, what does a concept do? A concept essentially takes each object and assigns it a label. It can call it belongs to the concept or not. Oftentimes, I like to think it as the concept colors them in one of 2 colors. So green if it belongs to the concept, and red if it does not belong to the concept, right? So now I have not told you what that concept really means, right? But there is some concept, and its job, it's a mathematical function, just takes a card and colors it or labels it and so on, right? You can also think of a concept as an operator that operates on this entire X set and just divides it into 2 parts. Objects that belong to the concept and objects that do not, right? That's also easy. So let's say that I am playing the role of Mother Nature, who knows the concept, right? So the role of Mother Nature is that it is going to color these according to the concept or not, right? So it will, Mother Nature is not going to tell you what the concept is. All it's going to do is it's going to color it in two colors. Green. I borrowed my daughter's crayons for this. There's a red. You can see she loves red by the amount of wear there, but not green. All right. So yeah, I was what? Mother Nature, right? So I'm going to just, so Mother Nature is going to just sort of, say this one is green, this one is red. Using some process, of course. Something is going on in her head, right? But not telling you. So just going to do all of these, and I'm not going to do all of these really, but let's say it does all of these, right? Now what happens in machine learning is that it will give you some of these, right? So it will give you maybe this one, and they'll all be labeled. This one, maybe this one, and this one. So it'll give you 5 of these objects out of the 16 that are possible, and they all are labeled. So this is our training data set, and our job is to infer what was that concept that was used to color these, and then once we know that, then we take a new data object, this one, and now we can color it accordingly, right? So that is the learning, the concept learning task, that from a subset of data objects which are labeled, I need to infer what was that concept, right? And then basically I use it for prediction, right? So is that clear so far? Vaguely? Okay. So now we need to figure out, okay, how do you learn that? How do you make a machine learn that? Maybe we as humans can, but how do we make a machine do this, right? So of course, let me tell you, just right away, it's a pretty challenging task, right? Because let's first see how many possible concepts can there be, right? So as I told you, the task of a concept is to color objects in one of the 2 colors, right? So how many possible concepts can there be if you just think of it as a mathematical operation? Another way to think about it is that it essentially breaks a data set into 2 parts, right? So how many ways can you break 16 objects into 2 sets? How many? You'll have to be a little louder. Right. 16. Right. No. You don't have to pick 2 objects from here. What you have to do is you have to take these 16 objects and divide it into 2 sets, right? So one possibility is that I put nothing in one set, put everything in another. One possibility is I can take 1 here and put 15 here, but I can choose that one in 16 ways, right? So there could be 2 to the power 16 possibilities. That means that there can be possible concepts 2 power 16. There cannot be any more, right? That's the way, these are the number of ways you can divide a data set, right? So if we just want to generalize a little bit, so let's say instead of 4 variables or 4 features, if our data is defined using d binary variables, then you can have 2 power d objects. That means that you can have 2 power d possible concepts, right? For d binary features, we can have these many possible number of concepts, right? So the machine learning algorithm's task is to look in this space and find the right concept, right? It's pretty challenging. Even for a very simple data set that's defined using 4 features, which are binary, suddenly you are looking at a space which is 2 power 16, right? So it's a huge space. I'm going to draw it like this. So this is my entire concept space. So think of it as all the possible ways you can do this. It's all gone in here, right? So machine learning algorithm has to go and search for the right one here, which becomes fairly challenging, even for this simple setting, right? So this is where we make our first assumption, right? We make our first assumption about the nature of the concept, okay? We are going to, what we are going to do is, we are going to make an assumption which will reduce the space that we want to look at. What the assumption that we are going to make is that our concept is of certain form, and I'll tell you what that form is. But the effect that that has is that suddenly your concept will, your concept space, we call it the space in which our concept lies, is reduced. Yeah, and that lets us sort of discover the right one more efficiently. Okay, and this is also known as, and I think we'll talk about it later as well, that this reduction from this large concept space to a small target concept space is what we know as inductive bias. So this is sort of an assumption that we put in to make the job of the learning algorithm easier. And every machine learning algorithm does that. The point is that if your concept space is this large, 2 power 16, it turns out that you will need all of your data to learn that concept. That means you will need all these 16 cards labeled, right? Which means that there is no point, because you already know in your training data what is the class of every possible object, right? So that kind of defeats the whole purpose. So in this case, what we are going to do is we are going to make an inductive bias to essentially reduce the space that we are going to look at. So how are we going to do that is what I'm going to tell you now. Any questions so far? Yes. Oh, why is that number 2 power 16? Well, so the idea of, so as I said, right, a concept, the job of a concept, or you can think of a concept as a mathematical operation which labels every data object as in one of the two cases. Like either it will say that this object belongs to the concept or it does not, right? So how many ways can you color 16 balls using 2 colors, or 16 cards using 2 colors, right? So I can color this in as whatever, red or green, right? Or I can call it belongs or not belongs. I can color this in 2 ways, color this in 2 ways, and so on. So 2 times 2 times 2 times 2, all the way to 16, hence 2 power 16. And the number 16 comes because 16 is the space of our, is the size of our concept space, and that is because we have 4 binary features, right? In another setting, the number of features might change, which means that the size of this would change, which means this would change. In some setting, instead of each feature taking 2 values, it could take 3 values, right? In which case your size of X would accordingly change, and I think you can work it out, and so on. So in fact, in the next gradients quiz, there's one problem like that, which will help you work this out. All right, so that's the, so yeah. So now we are going to figure out how to reduce our search space so that we can actually learn something meaningful, right? So the first thing we are going to do is we are going to say that our concepts are of a very particular form called conjunctive concepts. And don't worry about it right away. I'm going to explain it. All right. But before understanding conjunctive concepts, I need to tell you a little bit about our representation. Okay. So remember, every object X, right, can be written as like I wrote here, right? Circular, small, dark, irregular, right? So I can write it in a line as a vector with 4 values: circular, small, dark, and irregular. Right? So that's a representation, but I don't want to write so much. So what I'm going to say is that I'm going to write it like this: circular, large. So I'm going to call circular as 1 and oval as 0. Yeah, and I'm going to call a large as 1, and this is just sort of notation, right? There's nothing very serious going on here. Dark 1 and a light 0, and I'm going to write smooth as 1 and irregular as 0, right? So that way I can write x a little more succinctly. So I'm going to write it as 1 0 1 0, right? So that's just a sort of a binary notation, just to make my life easier. Don't want to write too much, right? So another object could be, I can write, so this, I can call this x1, this is object number 1. X2 could be 0 0 1 1, and you can read from here what it really means. Yeah, the reason I'm saying that is because then you can think of these as, you know, literals, binary literals, which can take 1 or 0, right? So you can apply mathematical logic on this, and that will make it easy, right? So let's say our objects are denoted like this. So we have 16 objects. So a concept, you can think of a conjunctive concept as a mathematical function which takes conjunction of few of these, right? You know what a conjunction is? Conjunction is just an logical and, right? Logical and, right? So you can think of this as and I need to use my slide, because one thing that I don't want to do is vary in the notation. Right. Yeah. So what you can think of a conjunction is basically a conjunctive concept is a subset of all possible features that you have, right? And it does sort of an and of these. So one example of a conjunctive concept could be circular and smooth. Okay, so the reason I call this a concept is that now if you take an object like this one, right, you can apply this concept to that and figure out if it belongs to the concept or not, because if both of these are true, only then it will belong. So this will not, right? It is circular, but it is not smooth, it's irregular, right? So this will not belong to the concept. This one will, this one will not, right? So on. So another example could be circular, let's take something else, large and light and irregular. So it is going to only consider those objects as green or belong to the concept who have these things present, right? You see what I mean? So it's essentially an application of a conjunctive rule on your objects. Yeah. So let's say so this could also be a particular concept, which is circular and large and dark and irregular. So a question for you all is, can you tell me how many objects will this concept label as green or belongs to the just one? Because there can be only one object that really sort of satisfies all of these, right? However, if I take another one which is just oval, I didn't hear you. 8, right? Yeah, somehow I thought, sorry, 3. So this is only 1. This is of course 8, because 8 of objects will have this true, right? There can also, so we can also write it, you know, a little more elegantly, I suppose. To use a pen. So we can also write it like this. So we will always have 4, because there are 4 features, 4 locations, and it will be and, okay? But so circular and smooth can also be written as circular and question mark, because we don't care about that particular feature. We don't care about this one, and smooth. right? So that's just another way so that every concept can be written as 4 things, but some could be question marks, some could be like this, right? So that is just a notation thing. So there are some special conjunctive concepts as well. So for example, a concept which is this: question mark and question mark and question mark and question mark. Can someone venture a guess what effect will this have? Everything will be considered as part of the concept, right? Because it doesn't care about anything. It's just like anything comes, I'm going to call you part of the concept, right? There's one more special concept which cannot be written like this, but we write it like this, okay? This is a concept which rejects everything, which essentially calls everything not part of the concept, okay? So we are going to call this particular concept as accept all, and this is we're going to call reject all. So this is going to reject no matter what you are, right? Whatever your shape is or whatever your features are, I'm going to call everything red, right? And the other one is that accept all. It's all kind of, so there are people like that as well, right? Some people just believe in everything, and there are people who don't believe in anything at all, and then there are people in the middle. Yeah. So anyway, so there are a lot of conjunctive concepts. So the next exercise that we are going to do is how many conjunctive concepts can there be if you have 4 features and all 4 are binary. So this could sort of help you. Can anyone sort of take a guess? Right. So you can have, see, for every position you can have 3 possibilities, right? It could either be one of the value or the other value or a question mark. So 3. For the other one also 3 times 3 times 3, that many. But there is this reject all which is special, which doesn't sort of come into this operation. There's +1, right? So in general, if we have d binary features, right, then we will have 3 power d plus 1 conjunctive concepts. All right. So that is, any questions about that? Okay. So which means that now let's look at this, right? This was for our example. So this is what 82, right? So suddenly, if you look, go back to our original thing, our total number of concepts was 2 power 16, right? Which is a large number. Anyway, but the number of conjunctive concepts is just 82, right? So suddenly we have made our problem much simpler by assuming that the concept that we are trying to learn, the target concept, is conjunctive. We have shrunk our search space. Okay, so we also sometimes call that space, that conjunctive concept space, as hypothesis space, because what we say is, because that's our hypothesis, right? Our hypothesis is that our target concept lies here, okay, and we assume that it is true, right? So now our job is to search for our target concept in this hypothesis space. Yeah. We could have other, and we will see that in a couple of classes, we can make other kinds of these assumptions. Instead of saying it's conjunctive, we can say let's have only disjunctive or things like that, right? So accordingly your space will change, and then you will only search for that. The reason we did that was that by doing conjunctive concepts, we can come up with very easy algorithms to learn the actual concept, right? So let's look at the first algorithm that we can apply to learn a conjunctive concept. But before moving, I just want to make sure that everyone is clear on conjunctive concepts. Yes, go ahead. There could be? Okay. So the question is, how did we arrive at this 82 or 3 power d plus 1, right? So let's go. So for that, let's look at how we represent a conjunctive concept, right? So remember, a conjunctive concept is essentially a subset of feature values that you sort of do an AND of, right? So as I told you earlier, we can represent every concept as these 4 place marks, and then we can put stuff there. So if your concept has circular, then you put circular here. If it has nothing for this particular feature, then put a question mark, and so on, right? So which means that this looks like this. Oval will look like this. So it will be oval and question mark and question mark and question mark, right? So this is this one, and so you can write. So now what we want to figure out is how many different types of these things can we write, right? So to do that, what we can look at it this way. So every position we can either have one of the 2 values because it's a binary feature, or a question mark, right? So we can do that for everything. So you can have 3 possibilities times d, whatever your d is. Oh, did I write? Yeah, 3 raised to power d, right? So, and then there is one particular concept which you cannot write in this form, right? Which rejects everything. So we always have that as special. So that way we have these many conjunctive concepts. Yeah. For D features. See, this is very specific to when you have 4 features, because the first position you can replace in 3 ways. This one you can do 3 things, and so on. But if you have D, then essentially you have D place values. So then you'll have this. So this is a general expression if you have D binary features. Any other question? All right. So now let's look at our first algorithm. So before that, we need to figure out what our problem setting is, right? So I'm going to switch to my slides. I don't want to write that much, but let's go back here. So I gave you an example, of course, right? So in the slides, you will see a very similar example, but in this, instead of just calling these as cards, I say, just to make it interesting, we'll say that our objects are actually tumors. Okay, so there are tumors in the brain, and they are described using 5. Here I just had 4 because 4 was the number of cards I wanted to cut, 16. But here, let's say there's one more, which is just the thickness. So we had shape, size, color, surface, and thickness. So we have 5 features, or 5. Here I say attributes, but that's fine. Okay, so 5 features, right? Each is binary. So our D is 5 now. We have a concept which is a malignant tumor, just to make it a little interesting. So it's still the same concept, right? It will call some tumors as malignant, some as benign, or one or another, right? And then we have basically we have some data and we want to learn everything, right? So we talked about all of this already. We talked about hypotheses, right? So now we have an algorithm, okay? So how does this algorithm work? We call this algorithm find S. It is there in the Tom Mitchell's book in chapter 2. So the idea is that you get some data, okay? And from that data, you try to learn your concept, okay? So we represent our concept as a letter C, because a concept is nothing but an operation that you're doing on the data, right? So every training data point that we get is your X, which is maybe one of these cards, and the label. So we write it as C of X. So basically, the mother nature has told you what C of X is. It's not telling you what C is. That's what you have to learn. But it is telling you for this X, what is C of X. So that's our training data. So this is our data object, and this is the label. Okay. Now we first assume that our target concept is the reject all, because in the beginning we have not seen any data at all, right? We don't know anything about malignant or benign tumors. So let's say it's a human who's trying to learn this, right? And let's say the human has become a radiologist for some reason, and now the human is looking at tumors, right? So it looks, in the beginning the human has not looked at any tumors, and that person has no background about what tumors look like, so very vanilla person. So in the beginning, and it makes sense, is that it's going to reject everything. It's not going to call anything as a tumor, or as a malignant tumor, sorry. It's going to accept nothing. So that's our starting, right? Then what we do is we look at the first training data that I get, and then I see what is its label. So if it's 0, which means it's benign or it does not belong to the concept, then I discard it. I do not update my target concept, right? I'm going to say my H will stay what it is. If if it is 1, right, which means that it is a malignant tumor or it's a green colored card, then I'm going to update my hypothesis. So I'm going to make it, the H becomes H pairwise and with my data object, and we'll go through an example for this, but there are some rules about this. So let's go through an example that will make it more clear. Okay, but anyway, so what it does is that as it gets data, it keeps refining that concept that's trying to learn, and once the data is done, it will stop and say, here is your target concept. Okay, so let's just run through a data, one particular example that will make it easy. Okay, so let's say this is the target concept that we want to learn. In reality, we won't know it, but just for an example, I'm telling you. No, not this. So I guess. Right, so let's do an example. Let's do an example on this to make it easier. And yeah, here we are. All right. So find S example. It's actually a pretty intuitive algorithm. I'm just making it sound more complex than it is, but just for the heck of it, let's do it, right? So let's say that, let's go back to our original example. Let's say our data is represented using 4 features, okay? And let's say our true concept is actually, so this is our true concept that we want to learn. It's conjunctive, of course, is just circular and small. Okay, so that is our true concept, which means that we can, this will be green. This will be green, circular and small. Circular and large will be red. Good. Circular and large will be red again. And circular, oh, again. And this will be green, right? And then others will be colored as well. But let's say this is our training data. Okay? Let's have one more. And of course, oval and large, let's take one more. It will be red. Okay. So let's do this. So we are going to run our algorithm through this. So in the beginning, our target hypothesis, of course, is reject all. I'm going to call everything as not belonging to the concept, right? Now let's just shuffle it a little bit. So the first object that I get is this, all right? So this is my X, and this is C of X, right? Because it's telling it belongs to the concept. So if it belongs to the concept, the algorithm says that change your H. So in this case, C of X is 1, right? Because it belongs to the concept. So what I'm going to do is I'm going to change my H to H and pairwise and with this X, right? So how do we do that? So in the beginning, H is just phi, or we can just write 4 phis here for each location, and X is circular, small, large, and smooth, right? I'm sorry? Okay, small. Oh, I see. Sorry. All right, you're right. Let's call it. Ooh, okay. Yeah, let's make it dark maybe. I don't know if it'll repeat something, but and this one will be light, right? Oh, I mean, I hope that's what it is. But anyway, yeah, right. So this is our training data. Which one was our first one? I forgot. Yes. Reject all means, so it's a hypothesis, right? Or a concept. So its effect is that it's going to label everything as not belong to the concept.
But what if just one of the entities, like the shape, does not belong to concept, and all the other things belong to concept? That means just one is reject and all the others are from our concept, right? So what about that?
No, so that will be a different concept, right? So going back to your example, let's say there's a concept which is like this: circular and large and question mark and smooth, right? Is that what you're saying? Oh no, right. So, sorry. So yeah, good point. I think if there is a reject anywhere, then it's a reject everywhere. See what I mean? Because if it's going to reject on any value of this, that means it will reject every object there, right? It doesn't matter what the other things are. That's why I typically write the reject all as only one this. But here, just because I want to do a pairwise and, that's why I wrote it here. You see what I mean? See, because you cannot have a reject option in one place and something others here, because it's going to reject it anyway, right? So those are not valid concepts.
So the concept that one is that outside concept, that's basically what.
Well, it's a special concept that we have added. It cannot be represented in this form. See, here, because what I don't want to do is that to say is that this can be replaced by circular or oval or question mark or phi. Because once you have a phi, then all the other things don't matter. So that's why I just have it as a special concept. So there are three possibilities plus one extra coming out from outside. See what I mean?
Yeah, that means that let's say something other than circular if the shape is square, then that is a case of rejected.
No. Here we are still assuming that it can only take two values. What reject does is that it calls it not belongs to the concept regardless of what the value is. Right? So think of it that way. So you can call something, let's say there is only one feature. So you can call it belongs to the concept if it has a particular value or the other value, or you can call it belongs to the concept if it has any value, right? That's a question mark. Or you can call it not belong to the concept if it has, regardless of what that value is. Right? And once you call something using one of the features, then it doesn't matter what the other features are. So that's why we have that as an extra, as a special concept. We can talk more after this. Just to, I see that you're still not sure. So we'll look at it. Okay. But so here the idea is like going back to our example, right? So this was our hypothesis in the previous iteration, and now this is a new data point, and because its concept, it belongs to the concept, I'm going to do a pairwise AND. So pairwise AND, in the case of if it is phi, then I'm just going to write circular. That's just a special thing that I'm saying. If it's this small, this is large, light. That's why I have this issue. Light, and then this is smooth. Okay, so that's sort of the rules if one of the literal is a phi, just for this case, right? So if you think, what we have done essentially here is that in the beginning I was calling everything as not belong to the concept. I was calling everything as a benign tumor, right? Because I didn't know anything. But now suddenly I saw this example, and this example is it belongs to the concept. So now what I do is that since I've only seen one, I'm going to say that any example that looks exactly like this belongs to the concept, right? Anything else still does not belong to the concept, right? Now what happens in this algorithm is the next data point comes. This one does not belong to the concept, which means C of X is 0, which means that you ignore it, right? So ignore this, we ignore this, we ignore this. It basically ignores, ignore everything. I need one more. It's crazy. There was one more. Oh, in my hand. Sorry. Yeah. So let's say, so it ignores all this. Then this one comes, right? So now our H is this, and this one is circular, small. How come this is the same as that? Oh, this one was the one that, sorry. This one came. So this one is circular, small, dark, and irregular, right? So this is our new X. And this is the C of X, of course, is 1. So according to the algorithm, I'm going to do the pairwise AND. So pairwise AND, if they do not match, then you make it a question mark. Okay, so circular, circular is fine. So you're going to replace it with circular, small, 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 light and dark. They do not agree there. So you're going to replace it with question mark, smooth and irregular, question mark. And if the data is done, then you stop there, right? And then you say that this is my target concept, right? So if you think about it, the way humans work is that all you have done is that in the beginning, you didn't know anything, so you called everything as benign. Then you saw the first malignant tumor, and you said, okay, I'm going to only call other tumors that look exactly like this as malignant and nothing else. Then you saw the next malignant tumor, and you saw that these things were common, right? So you said, okay, this means that in all malignant tumors I've seen so far, these two features take these values. So I'm going to keep that in my target concept, but these ones do not. So I'm going to ignore that, right? It's logical, right? There's no question about any ambiguity there. And then you stop, okay? And in this case, it turns out that after looking at this data, we were able to actually learn the actual concept, right? This was the true concept. So, but for the FindS algorithm, it is not always certain that it will learn it, right? For example, even in this case, if my training data didn't have this particular object, so it just had these 5, right? So you could work that out, right? First time it would have learned this as your target concept, and after that you would not have updated it, right? Which means that it would have just stuck with this one, so which is clearly not the true concept. Yeah. So it's not necessary that your FindS algorithm will always learn the true concept. It depends on what data you get. Is a question there? Yeah. You, right, so good point. So the question is that why are we ignoring the negative objects, right? And the answer is that for this, and that's because this is what this algorithm does, right? It's just the property of this algorithm. So technically, you should not ignore them. And in fact, the next algorithm that we'll see on Monday will use those as well, all right? So what we are going to do next, of course, we don't have time now, but when we start the next class, I'm going to quickly tell you why this is a very crappy algorithm, because it does not guarantee that it will learn the right answer. Plus, we will also see that it takes a lot of time. And then we will move to another algorithm, which looks at both types of objects, and it's a little more advanced. And we'll take baby steps, and soon we'll be just flying in the sky. All right, any other questions? All right, thank you very much. Have a great weekend. I'll see you on Monday. Dave, could you switch that off? Thank you.